Everyone. Thank you for taking the time out of your day to check out my poster presentation. My name is Sean McBride, and I will be presenting on the differential physiological responses to heat and drought stress for annual bluegrass and creeping bentgrass. Here's the introduction, which you are more than welcome to look into and read on your own if you're interested. What it ultimately is saying is that annual bluegrass is a cool season grass that has very low tolerance to drought and heat stress. The physiological mechanisms involved that govern this type of ill response of POA to these stresses they're not really well understood. So what this study is going to do, and what we did here, is that we looked at drought and heat stress individually in POA annual to better understand the different physiological responses POA has to them. And then we compared POA's responses to those of creeping bentgrass, a cool season turfgrass species that exhibits, relatively better tolerance than POA, to help develop more efficient management strategies for courses where POA and creeping bentgrass are co-present. Okay, so how did we do this? That brings us to the materials and methods. We collected sod pieces of POA and creeping bentgrass from the field, placed them in plastic bins filled with fritted clay, where each bin had 3 sod pieces of POA and 3 sod pieces of creeping bentgrass, arranged in an alternating order. And then they were arranged into 3 stress treatment groups. Our first treatment group was the control group, subjected to optimal growth temperatures and were well watered. Our drought stress group was subjected to optimum growth temperatures but were left unwatered for a period of 21 days, and our heat stress group was subjected to heat stress temperatures and were well watered for a total of 42 days. After 21 days of drought stress, we rewatered the drought stress treatment group, and they entered into a 21 days of drought stress recovery. Over the course of this 42-day study, we took measurements weekly, including turf visual quality, percent green canopy cover, electrolyte leakage, leaf relative water content, and canopy temperatures. Here's a quick summary of the results from what we found over the course of the study. First, we found that both POA and bentgrass suffered more serious stress under drought conditions compared to heat stress. Of the two, POA experienced a greater decline in turf quality under both heat and drought stress compared to bentgrass, and upon rewatering, the drought stress bentgrass plants recovered faster than POA. Right, and that brings us to our first figure, which is a series of images here depicting the progression of stress and recovery in keeping bentgrass throughout the study. The first row has our control plants, second row has our heat stress plants, and our third row has the drought stress plants. Here at the bottom indicates the time at which each of these pictures were taken, and what you can see is that the heat stress plants slow a gradual decline in turf quality and increase in what appears to be leaf senescence. Drought stress plants during the drought period also saw this decline, but if you compare the two, you'll see that while under drought stress, creeping bentgrass shows more severe leaf senescence and maybe wilting compared to the heat stress plants here. After rewatering, which began after 21 days of drought stress, you can see a slight increase in turf quality and some recovery throughout this time period here. Alright, here we have a similar figure or set of images, this time depicting the progression of stress and recovery in POA. We have our control at the top again, heat in the middle, and drought on the bottom. And you see a very similar trend as you did in creeping bentgrass, where as the heat stress period goes on, there's a greater decline in turf quality within the POA. Same could be said for drought stress. And if you compare drought stress to heat stress, you'll see that the drought stress plants showed greater signs of leaf senescence and wilting than the heat stress plants did. After rewatering of the drought stress plants, we'll see a slight, a bit of recovery. It's not as obvious, I think, as creeping bentgrass, and we'll take a look at that in the next slide. Okay, so here we have those two figures this time in a frame for you to see both of them together. And what you can really look at here is that if you look at the heat stress POA and you look at the creeping bentgrass heat stress plants, you'll see that POA shows more leaf senescence and more severe leaf senescence over the heat stress period. And if you look at the recovery period for the drought stress plants in both species, what you can see is that creeping bentgrass seems to have recovered faster and to a better extent than POA did down here. Alright, and now we're going to move over to the left here and take a look at the various figures displaying the data of the different physiological measure or parameters we measured that I mentioned in the materials and methods section. Here is the first set of figures depicting turf quality for both creeping bentgrass on the left and POA annua on the right. The x-axis indicates the days after stresses were imposed. The y-axis shows you the turf quality rating average at those days for each control group or treatment group. And what you can look at, if you take a look at each graph separately, you'll see that under drought stress, especially at day 21, there's a much greater decline in turf quality than under heat stress. That's true for creeping bentgrass and for POA. What you can also do is if you compare the turf quality values for heat and drought stress to the control, you can see relatively which one is more affected by these stresses. So by doing this, we were able to conclude that creeping bentgrass was maintained at relatively higher turf quality during heat stress after 21 days. So let's take a look at 21 days here. Let's take a look at heat stress in the gray compared to the control values in creeping bentgrass, and you see it's a little bit lower, but not to the same extent as POA, where heat stress values are relatively lower than the control. You can see a similar thing happen at 14 days drought stress, where there's a bit of a decline in turf quality here compared to the control for creeping bentgrass. It's the same thing as seen in POA, but the degree in which these are lower differs, and it's more severe in POA. Last that we'll look on these set of figures is how they responded to rewatering after drought stress, and we'll see that, relatively speaking again, creeping bentgrass recovered faster than POA did. The next set of graphs we look at is percent green canopy cover, and you'll see a very similar relationship or trends where drought was more effective or caused more severe damages than heat stress, and that creeping bentgrass was able to maintain relatively greener turf compared to POA during heat stress throughout days 28 to 42 and at 14 days drought stress as well, where if you look, you can clearly see that the values in turf quality or percent green canopy cover does not differ too much at this date in creeping bentgrass, but for POA there's more of a difference, and percent green canopy cover is a bit lower, relatively speaking. Here's our next set of figures. The first one on the top here depicts changes in electrolyte leakage throughout the study for creeping bentgrass and POA. And electrolyte leakage is an indication of cell membrane stability. The greater the electrolyte leakage, the more damage caused to cell membranes throughout the stress period. And what we'll see again is the same trends we saw before. There's greater electrolyte leakage indicating greater damage for drought stress plants compared to heat stress plants in both species. And if you were to compare those values of drought stress and heat stress to the control, you'll see that creeping bentgrass was able to maintain higher cell membrane stability under drought and heat stress, and actually recovered faster upon rewatering compared to POA. This is very clear for heat stress, where all the way up to day 35, there's relatively little difference in electrolyte leakage between heat stress and control plants, while POA, you can see that these values are diverging much sooner, all the way as early as 21 days, where you're getting significant increases in electrolyte leakage from heat stress plants compared to control stress plants. Then this next set of figures displays the relative water content throughout the study. And ultimately what we're seeing is that during drought, POA exhibited an early and greater decline in relative water content compared to creeping bentgrass. Under drought, which is seen at day 14, where the relative water content in POA has a greater gap and is lower relative to the control compared to creeping bentgrass. And it's also seen for the heat stress treatments throughout the period of 14 days heat stress to 21 days heat stress, where there's relatively little differences between the two values in creeping bentgrass, but in POA you see that is significantly lower. Us to our final figure here, showing canopy temperatures of the two species of grasses at certain times during the two stresses. Here we have bentgrass at the top, POA at the bottom, and on the left side shows you the canopy temperatures at 28 days heat stress. On the right side you show canopy temperatures at 21 days drought stress. The canopy temperature is indicated by this bar here, where higher temperatures are represented by lighter colors and cooler temperatures are represented by darker colors. So from this, what we can see is that under heat stress, POA annua was able to maintain cooler canopy temperatures, indicated by this darker blue color, compared to bentgrass. But under drought stress, the opposite is true, and bentgrass has the cooler canopy temperatures. Alright, and that brings us to our conclusions and discussions. Like we said before, both creeping bentgrass and POA showed greater damages under drought stress compared to heat stress. Of the two, POA showed greater declines in turf quality under both stresses. However, what was interesting to note is that under heat stress, POA was able to maintain lower canopy temperatures, potentially due to transpirational cooling. But under drought stress, where water isn't available, bentgrass had the relatively cooler canopies. What this might indicate is that POA's low tolerance to summer stress may be related to an inability to effectively conserve water under these stresses, leading to high transpiration rates while water is available. However, when water is no longer available, plants suffer lower relative water contents and eventual physiological damages. And that concludes my poster presentation. Here's the full poster again to finish it up. Thank you for listening, and I hope you enjoy the symposium to its fullest.